welcome you all to this digital classroom for the subject control systems. In the previous class, we discussed about rule number 8 for the construction of root locus subjected to the calculation of angle of departure for a complex pole as well as angle of arrival for a complex zero. And today, we are going to solve few example problems related to the construction of root locus which has been taken from previous year's VG question paper. Let us take this example problem. Sketch the complete root locus of system having g of s into h of s is equal to k divided by s into s plus 1 into s plus 2 into s plus 3. So you are given with a open loop transfer function g of s into h of s. And with respect to the given data, we have to sketch the complete root locus. Now, let us follow the general steps to be followed to solve the problems related to root locus. As we very well know that the root locus is always symmetrical about real axis. This is the first statement subjected to rule number 1. Now let us start to solve the problem. Step number 1 is to get the general information about the number of poles, zeros and number of branches from the given g of s into h of s. That is from the open loop transfer function that is given in the question. We have to calculate the number of open loop poles and number of open loop zeros as well as the number of branches. That the number of zeros z is equal to 0, and from the denominator polynomial we could able to see that we have poles at s is equal to 0, then s plus 1 equal to 0, hence we have a pole at s is equal to minus 1. Then equating s plus 2 equal to 0, we get a pole at s is equal to minus 2. Then by equating s plus 3 equal to 0, we get another pole at s is equal to minus 3. Hence we have 1, 2, 3, 4. 4 poles. Hence P will be equal to 4 and Z will be equal to 0. That is number of poles P equal to 4 and number of zeros Z is equal to 0. And we have already discussed that if P greater than Z, then P will be equal to N. That is, the number of branches will be equal to P. Hence, N will be equal to 4 in this example. So we have collected few of the general information from the given question. With respect to rule number 2, we know that the branches will start from an open loop pole and it will be terminating at an open loop zeros. When k is equal to 0, it starts from an open loop pole, and when k is equal to infinity, it terminates at open loop 0. Hence, in this example, the starting point is at open loop poles at s is equal to 0, s is equal to minus 1, s is equal to minus 2 and s is equal to minus 3. And the terminating point, we know the procedure. P poles will be terminating at Z zeros. 4 poles has to be terminated at Z zeros. As we don't have any zeros here, we know the continuity of the rule number 2, that is P minus Z branches will be terminating to infinity. In this example, P is equal to 4 and Z is equal to 0. So all the 4 branches which is emerging from the 4 poles will be terminating to infinity. Hence the terminating point is given by s is equal to infinity, minus 1 reaches infinity, minus 2 reaches infinity and minus 3 reaches infinity. Hence in this case all the branches approaching to infinity. Now let us plot the open loop poles at s is equal to 0, s is equal to -1, s is equal to -2, and at s is equal to -3. After drawing the pole 0 plot, we have to identify the existence of the root locus, as well as we have to predict the minimum number of breakaway points by using a general prediction method. So step 2 is subjected to existence of root locus. From the S-plane, after drawing the pole 0 plot from the given question, now we have to find the existence of root locus. We know the procedure. First, we have to take any point in the positive real axis, look towards the right. Can you able to see any odd number of poles and zeros towards your right? No. Then root locus does not exist. Now let me take a point here in the negative real axis. Let me look towards the right side. Now put up the same question. Can you able to see any odd number of poles and zeros towards your right? Yes, of course, I could able to see one number of pole towards my right. Hence, root locus exists towards the left of an odd number of poles. Now let us take a point here in this location and look towards your right and ask the same question. Can you able to see any odd number of poles and zeros towards your right? We have a count of 2, that is even number. Now the answer is no. Hence, root locus does not exist in this region NRL. And here you can write it as root locus exists in this region, that is RL. Now let me take a point here and now look towards your right and ask the same question. Can you able to see any odd number of poles and zeros towards your right? Yes, now the count is 1, 2, 3. That is odd number of poles and zeros. Hence, a root locus exists towards the left of a odd number of poles and zeros. Hence, this region I can mark it as RL, that is a region of root locus. And let us highlight it. Then, let us assume that you have taken a point here. Look towards your right side, ask the same question. Do we have any odd number of poles and zeros towards your right? Now the count is 1, 2, 3, 4. That is even number. Hence, root locus does not exist in this region. Hence, and I can make it as NRL. Now we have identified the region of root locus. This region is NRL. And this region can be marked as RL. And this region can be marked as NRL. And this region can be marked as RL. And this region is NRL. Once after identifying the region of root locus, now we have to predict the minimum number of breakaway points by using general prediction method. Let me recall the rule. If we have any alternate poles and if it is in the region of root locus, then there exists minimum one breakaway point. This is what the rule says. So let us find out whether we have any alternate poles. In this case, we have a pair of alternate poles here and here and that is between -1 and 0, between -2 and -1, and between -3 and -2. These are the alternate poles. We have 3 combinations. And now the question is whether these alternate poles is a part of the root locus. Then it is very clear that -2, -1, this is not a part of the root locus. So this case can be excluded. Now we have only 2 possibilities. That is -1, 0 and -3, -2. So now again let me repeat the rule. That is, if we have any 2 alternate poles, yes, we have 2 alternate poles. And if it is in the region of root locus, yes, it is in the region of root locus, then there exists minimum one breakaway point. So here exists one minimum breakaway point, one breakaway point. Similarly, in this case, again here, let me repeat it once again. We have an alternate pole and it is in the region of root locus. Hence, there exists again here minimum one breakaway point. In use of the general prediction, we have identified a minimum of one breakaway point between -1 and 0 as well as -3 and -2. Hence, we can write it as minimum two breakaway point exists. One between s is equal to 0 and -1 and the second between s is equal to -2 and -3. Let us move on to the next step. Step 3 is to calculate the angle of asymptotes. So we know the formula to calculate the angle of asymptotes, which is given by theta equal to 2q plus 1 into 180 degree divided by p minus z, where q equals to 0, 1, 2, 3, so on extended up to p minus z minus 1. And the number of asymptotes is given by p minus z. As we have p is equal to 4 and z is equal to 0, in this case we will be getting 4 asymptotes. So q will be equal to 0, 1, 2 extended up to p minus z minus 1, p is 4, z is 0, minus 1. So 4 minus 1, it's 3. So q will be ranging from 0, 1, 2 to 3. Let us substitute for q equal to 0. Once after substituting for q equal to 0, we get theta is equal to 180 degree divided by 4 minus 0. Hence, theta 1 will be equal to 180 degree divided by 4, that is 45 degree. Now let us substitute for q is equal to 1. Once after substituting for q is equal to 1, theta will be equal to 2 plus 1, 3 into 180 degree divided by 4. Hence we get 135 degree. Now let us substitute q equal to 2 in the above expression. Once after substituting for q equal to 2 in the above expression, 2 into 2, 4 plus 1, that is 5 times of 180 degree divided by 4. Therefore, theta 3 will be equal to 225 degree. Finally, let us substitute q equal to 3 in this expression. So 2 into 3, 6 plus 1, 7 times of 180 degree divided by 4. Therefore, Q4 will be equal to 315 degree. As I told you, we get 4 asymptotes. That is, always you will be getting P minus Z asymptotes. So in this case, we have got 4 asymptotes. So we can write it as 4 branches approaching to infinity. Hence, 4 asymptotes are required. Step 4. Determine the centroid and sketch a separate sketch for step 3 and step 4. Once after calculating centroid, with centroid as a center, we have to mark all the asymptotes making use of the protractor, and we have to draw the asymptotes. Now let us calculate the centroid. We know the formula for centroid is given by sigma equal to summation real part of poles minus real part of zeros divided by p minus z. So the real part of poles, we have s is equal to 0, s is equal to minus 1, s is equal to minus 2 and s is equal to minus 3. Hence the summation of real part of zeros, so it is 0, minus 1, minus 2, minus 3, the sum of all, minus real part of 0. As we don't have any 0 in the numerator polynomial is nil there, hence summation of real part of 0 will be equal to 0 divided by p is 4 in this case and z is equal to 0. So we get minus 1, minus 2, minus 3 divided by 4. That is minus 6 divided by 4. We get the centroid as minus 1.5. Once after obtaining step 3 and step 4, we have to plot a separate graph with centroid as minus 1.5 as center, we have to draw the asymptotes. First, let me mark the centroid sigma exactly at minus 1.5. And now let me take a protractor and with minus 1.5, that is a centroid, as the center, we have to plot for 45 degree, 135 degree, 225 degree as well as 315 degree. So first let me mark for 45 degree. 45 degrees exactly here. So let us mark it. This is a plot for exact 45 degree. Then let us plot for 135 degree. 135 degrees exactly here. So let us mark for 135 degree. Now we have to mark for 225 degree. So this angle is 180 degree. This is 190. This is 200. This is 210. This is 220 and 225 degree. This is 225 degree exactly. I have marked for 225 degree. Now let us mark for 315 degree. This angle is exactly 270 degree. So 280, 290, 300, 310 and 315. This is exactly 315 degree. I marked for 315 degree also. Now let me take a ruler and join the lines. Now with centroid sigma is equal to minus 1.5 as a reference, let me plot the first set of asymptotes at theta is equal to 45 degree. Now again with sigma is equal to minus 1.5 as a reference, we have to draw the second asymptotes at an angle exactly at 135 degree. Again with sigma as center, exactly sigma is at minus 1.5. Now we are drawing the third asymptote, which is at an angle of 225 degree. Finally, the fourth asymptotes, let us follow the same procedure with sigma is equal to minus 1.5 as the center. Let us mark the third asymptote, which is at an angle of 315 degree. So this is exactly at 315 degree. Sigma as center. Let us mark for the third asymptotes, which is at an angle of 315 degree. Finally, now this shows the sketch for the centroid and the asymptotes at 45 degree, 135 degree, then at 225 degree, and finally at 315 degree. Step number 5 is to calculate the breakaway point. The root locus must have a breakaway point which can be found by solving. We know the steps to be followed to calculate the breakaway point. For a given g of s, we have to first write the characteristic equation which is given by 1 plus g of s into h of s equal to 0. Hence, let me substitute for g of s into h of s from the given question. Once after substitution, let us simplify this characteristic equation. After simplification, I get s to the power 4 plus 6s cube plus 11s square plus 6s plus k equal to 0. Once after writing the characteristic equation, we know the procedure. That is, we have to represent k in terms of the polynomial s. So I have taken k towards the left and I have shifted all the s terms towards the right side. And now the next step is to find dk by ds, and it has to be equated to 0. So let me differentiate k with respect to s. Once after differentiating, the first term will be minus 4s cube, and differentiation of minus 6x cube will be 18s square. Then the differentiation of minus 11s square is minus 22s. And the differentiation of minus 6s is given by minus 6. And we have to equate it to 0. And based upon the highest power of s, in this case the highest power of s is 3. Therefore, we will be getting 3 roots once after solving this equation. So final expression is 4s cube plus 18s square plus 22s plus 6 equal to. Once after solving this equation, we will be getting 3 roots. One at s is equal to minus 1.5 and the second one at minus 0.3881 and the third one at minus 2.619. Once after getting the breakaway points, we have to check for the validity of it. So minus 1.5 comes exactly in this region, and this is not valid because it is not in the region of root locus. So it is not valid. Whereas minus 0.381 comes exactly in this region and it is located in the region of root locus, hence this becomes valid. Also, minus 2.6119 comes exactly in this region between minus 2 and minus 3. Hence, this breakaway point becomes valid. So based upon the prediction which has been made with respect to step number 2, we have already predicted that there exists a minimum breakaway point between minus 1 and 0 as well as between minus 3 and minus 2. So now our prediction is right and we have checked for validity also and it has been proved in step number 5. So s is equal to minus 1.5 is not on the root locus and s is equal to minus 0.381 as well as minus 2.619 is on the root locus, that is the breakaway point. Moving on to the next step. Now let us calculate the intersection of the root locus with the imaginary axis. The first step to write the characteristic equation. We have found the characteristic equation already from step 5, so I can write it directly. The characteristic equation is given by s to the power 4 plus 6s cube plus 11s square plus 6s plus k equal to 0. Once after writing the characteristic equation, we have to generate the root array. So let me write the s coefficients of the first 2 rows can be filled out. S power 4 coefficient is 1 and s cube coefficient is 6 and s square coefficient is 11, s coefficient is 6 and we have k, then make it a 0. Once after filling the first 2 rows in the root array, we know to fill up the rest of the rows making use of the formula. For the third row, first element is given by 6 into 11 minus 1 into 6 divided by 6. Therefore, we get 10. Then for the third row, second element, we can make use of the pattern 6 into k minus 1 into 0 divided by 6. Therefore, it is k. And the third element will be equal to 0. Then to fill up the fourth row first element, we can make use of the formula 10 into 6 minus 6 into k divided by 10. Therefore, we get 60 minus 6k divided by 10. And the second element will be given by 10 into 0 minus 6 into 0 divided by 10. Therefore, it is 0. Finally, s to the power 0 row is given by 6 minus 6k divided by 10 into k minus 10 into 0 divided by 60 minus 6k divided by 10. So 60 minus 6k divided by 10 in the numerator and denominator will get cancelled out. Therefore, I get k here. Now we have to find the range of k. So from the last row, it is very clear that k should be greater than 0 so that the system will be in stable condition. Then making use of the s to the power 1 row, the first element can be given by 60 minus 6k divided by 10 greater than 0. Therefore, 60 minus 6k greater than 0. Hence, 60 will be greater than 6k. Therefore, 10, 60 divided by 6, we can write it as 10 greater than k. So, k is ranging from 0 less than k less than 10. Now, let me find k margin. So, it is very clear that k margin is equal to plus 10. When we substitute k margin in the s to the power 1 row in the place of k, now the expression will be 60 minus 6 into 10 divided by 10. 60 minus 60, this becomes 0. The first element has become 0. So this s to the power row now has become a complete 0 row, s to the power 1 row. So we know the procedure. That is, we have to take the row which is previous to the complete 0 row and we have to represent that a square row in the form of an auxiliary polynomial, and if you simplify the roots of the auxiliary polynomial and if you find the roots of the auxiliary polynomial, if there are roots present on the imaginary axis, which means that the system is going to become marginally stable. Let me write the auxiliary polynomial as 10s square plus k equal to 0. Let us substitute for k as 10. And that is the point at which the system will be marginally stable. At k is equal to 10, 10s square plus 10 equal to 0. Once after simplifying, 10s square will be equal to minus 10. Therefore, a square is equal to minus 1. Hence, s is equal to plus or minus j, which means that we have two roots on the imaginary axis. Therefore, at k is equal to 10, exactly the system is marginally stable. Let us move on to the next step. Step number 7 is not applicable as we don't have any complex conjugate poles or zeros with respect to the given g of s. Step number 7 becomes not applicable. Therefore, after examining step from number 1 up to step number 6, now we have enough information to draw the root locus plot. Therefore, let us plot the complete sketch of the root locus. We have identified the breakaway points, intersection of the roots on the imaginary axis at plus j and minus j, and we have marked with the centroid at minus 1.5 and the angle of asymptotes at 45 degree, 135 degree, 225 degree and 315 degree. So now there is enough information to draw the root locus plot. As we know that when k equal to 0, we have a pole at s is equal to -1 as well as at s is equal to 0. When you keep on increasing the value of k, we could able to see the movement of the poles in this region of the root locus. And these two poles will intersect at one particular point at which multiple poles occur at a particular value of k, and that is the place at which the breakaway point occurs. And now the branches will try to break away exactly at 90 degree. The angle is given by 180 degree divided by number of branches. As we have two branches in this case, this will break away exactly at 90 degree. So exactly at this point it will break away. And as the angle of asymptote is at 45 degree as well as 315 degree, this branch, once after k increases, it will reach the imaginary axis at k is equal to 10. We call it as a marginally stable state and we can mark it as k margin equals to 10. And when k exceeds 10, these roots crosses the imaginary axis and reaches the right half of the S-plane, which makes the system to be as unstable. And finally, it reaches infinity. And on the other side, at k is equal to 0, we have a pole at s is equal to -3 and s is equal to -2. And when k keeps on increasing, there will be a movement of these poles in this direction and they try to intersect at one particular point in which multiple pole occurs, and that is the point at which breakaway exists. And this branch will try to move in the path guided by the asymptote as at 135 degree as well as 225 degree. Therefore, the final plot can be given in this direction. From the breakaway point -0.35, it intersects on the imaginary axis and after k margin greater than 10, it increases, goes to the right side, which makes the system to be unstable and it tends to reach infinity. Similarly, on the other side, we have a breakaway point in which the branches break away and we could able to see that branches is reaching infinity. So all the 4 branches reaches infinity. Step number 9 is to predict the stability and the performance of the given system by using the root locus. When k ranges from 0 to 10, the system is absolutely stable. And when k equal to 10, the system is marginally stable. And for k greater than 10, the system becomes unstable. This is what we have to write for step number 9, speaking about the stability. And we can plot the complete root locus sketch. The final sketch with the direction of root movements as k increases from 0 to infinity is as shown here. So with the movement of the branches, with the arrow mark is as shown here. And on the other side for the other breakaway point, the moment is shown very clearly. For the breakaway point at -2.619. Let me show you the same output of the root locus making use of Matlab. For a given open loop transfer function, let us represent in terms of the polynomial. Once after simplifying the denominator, it will be of the form s power 4 plus 6s cube plus 11 square plus 6s. And now the numerator polynomial, we have 1, and in the denominator polynomial s power 4 coefficient is 1, then s cube coefficient is 6, s square coefficient is 11, and the s coefficient is 6, and we don't have any constant term. I can write it as 0. Now the Matlab command is very simple, or a locus of num comma 10. This is n. If you type this command, you can get the root locus plot very easily. Let us try doing it in Matlab. Let me click on this icon, Matlab, in the command window. Let me write the numerator polynomial num equal to 1. The denominator polynomial is given by s to the power 4. So s power 4 coefficient is 1. 6s cube. So s cube coefficient is 6. 11 square. 6s. And we have a constant 0. Therefore, we can make use of the command or locus of num comma 10. Now we can look into the plot. This plot is very clear here. We could able to see here a pole at the origin and another pole at -1 and another pole at s is equal to -2 and the other pole at s is equal to -3. And it is very clear here that when k increases, this is the point at which breakaway occurs. We check for validity and we have marked the breakaway point, in our case -0.3, and it breaks away and this branches is reaching infinity. Similarly, on the other side, for the branch which is moving from s is equal to 0, it reaches one particular point, breaks away, and then it is trying to reach infinity. Similarly, for s is equal to -2, when k increases, it reaches one point, and on the other side, when s is equal to -3, at k is equal to 0, it increases, both intersect at one particular point, reaches the breakaway point. Then this is breaking away and it is trying to reach infinity. And on the other side, this branch is trying to break away and try to reach infinity. Let us compare this output with our final plot. So the direction of the root's movement as k increases from 0 to infinity can be shown in this arrow mark. So for this pole at s is equal to -1, when k increases, it breaks away and it takes this direction and reaches infinity. As shown here, you could be able to see the movement. Similarly, on the other side, when s is equal to 0, breaks away and it tries to reach infinity, as shown here. And on the other side, when s is equal to -2, when k increases, it breaks away and it tries to reach infinity, the third branch. And it is very clearly seen here, as well as when s is equal to -3, k increases, breaks away, and it terminates at infinity, the fourth branch, which is seen very clearly in this case. So making use of the Matlab, we can try to get the output in one single shot and we can compare with your answers. In the next session, let us solve few more problems related to root locus. Thank you.